Hopefully. All right, we ready? Okay. Got some folks coming in. We'll wait for these folks. All right. Oh, we'll wait for James. Alrighty. And here we go. All right. Hello, everyone, and welcome. Hope that your World Water Week 2025 is going really well. Congratulations, you made it to the last session of the day today, and we'll try to keep it as energized as we can. I'm really excited. My name is Alex Johnson. I'm with Verity, and we've invited a really excellent panel of experts here on water quality monitoring technology, and we especially want to dive into what's been changing. What are the big updates in the last couple of years, and hopefully challenge some of these experts on what they see coming down the pipe in the next 5 to 10 as well. So very excited to get into it. Thank you so much, and we will jump right in. I am going to show you the agenda. Hopefully, you saw this in your program online. But essentially, we'll get through some introductions. I neglected to actually tell them this, but I'm going to pass it over to all of you to do a 1 or 2 minute introduction of yourself, so that I don't butcher it. And then we'll do it. It'll probably be a little bit longer than this. We'll go probably 8 to 10 minutes per person. They're going to present to you on some of their expertise, some of the projects that they've worked on that fall into this topic, and then we'd love to take a break and really engage you all to get some questions, and then we'll have a panel discussion. So I've got some facilitated questions, and then obviously based on what we hear from the crowd, we will guide our way through hopefully a very valuable hour and a half. So thank you again, and then would love to start with some questions for you, just so our presenters have a good understanding of who it is we are talking to. So would love some audience participation, and also welcome everyone online. I apologize that I can't see your hands, but in the room, do we have anybody representing research or academic institutions working on water quality? One, two, three. Okay, four. Thank you, sir. How about a technology company, developer, innovators? None of those in the room. Hopefully, some online. Are there any implementers of water quality or drinking water wash projects? Quite a few. Welcome. Any government agencies or utilities? Great, great. A couple. And how about multilateral or donor organization involved in water? None of those. Okay. Let's see. Anybody with lived experience managing water quality locally? Yes, sir. Welcome, welcome. All right, great. And then how about a different crosscut? Let's raise your hand if you are primarily focused on work in low and middle income countries. Quite a few. Okay. How about humanitarian or emergency response? Fair number. How about rural or remote areas? About half. And then switching over, how about those of you working in urban areas with an urban focus? Okay, got a couple. And then high income country folks focused on more developed applications. Great. All right, thank you very much. I feel like we know you better, and you're about to know all these folks well as well. I would just touch, for in terms of why am I here. So I'm the chief strategy officer for Verity. Verity is a climate and water tech startup based in Colorado, in the United States. But we work globally on water resilience, both wash, drinking water applications, as well as irrigation upgrades, ecosystem restoration, et cetera, and a lot of conservation finance, carbon finance, and what all of that has taught us over the years is that the financial opportunities are really only as good as your DMRV, your monitoring, reporting, and verification. And so at Verity, we're very, very excited about some of the newest emerging technologies because everything's getting cheaper. Therefore, you can put a lot more sensors out into the world, and with more data coming in, real-time sensor data, then you can also take advantage of some of the big data, machine learning analytics, and hopefully create a lot more value for the world than a chatbot. So we're excited about that, and we've worked in various ways with many of the folks on stage, and we're excited to bring some of their expertise to World Water Week this year. So thank you. We will jump right in with Megan Lindmark. Actually, I forgot the step. Let's go down. Yeah, let's go down the row first, and if everybody could spend a minute or two, would love to know your background as well as who you're working for currently.
Awesome. All right, everybody hear me okay? All the audience is sitting kind of on this side, so I apologize to the audience online that I'm like
if this was a ship, it would be listing like
a
this.
Crooked, but that's all right. So I'm Megan Lindmark, as Alex just said. I am the senior technical program director for COVA. COVA is a nonprofit social enterprise working on improving access to safe drinking water across rural communities in Central America. And I'll get into more of our work momentarily. And I am also the CEO and co-founder of a nonprofit organization, Mangrove Water, working to provide technical assistance to inline chlorinator implementers globally. So my background, I'm an environmental engineer. I have my PhD in environmental engineering from the University of Iowa. Go Hawks, if anybody is in the audience. But yeah, I'll get in more about my background and our work in Central America momentarily.
Thank you. I'm James Sorensen. I'm a senior hydrogeologist at the British Geological Survey and have spent about the last 12 years working on tryptophan-like fluorescence as a real-time indicator of fecal contamination risks, both in Africa, India, and in Europe as well.
Hello, everyone. My name is Whitney Knope. I am a PhD student in environmental engineering at the University of Colorado Boulder in the US, and I am also an environmental engineer with Verity. And my research primarily focuses on monitoring drinking water quality and applying technologies to improve the spatial and temporal density of water quality data and making that actionable.
Hi, everyone. I'm Elena Harkness. For the last 6 years, I've served as the CEO of Current. We're a nonprofit water innovation hub headquartered in Chicago. And for the last 18 months, I've also served as the CEO and principal investigator for an initiative called Great Lakes Renew, which is a National Science Foundation-backed regional innovation engine for the Great Lakes. I'm really excited to be here. My background's actually in urban economic development and public policy, and I've been really excited about this opportunity to talk about the intersection of sort of urban development goals and water in this context. I'll be sharing a little bit more about our work on real-time water quality monitoring in our Chicago River and our testbed network across the Great Lakes.
Thank you so much. And yeah, as you hear, we're going to kind of work across the low, middle, and high income strata, and hopefully draw some really interesting new insights around how emerging water quality technologies, monitoring technologies can be applied. So here we go.
All right. Yeah, we got the introduction out of the way, and I apologize for the overlapping words on the slides here.
Oh, sorry about that.
No, probably my bad. So either way, so as I mentioned, COVA is a nonprofit working in Central America, providing support for inline chlorination in rural communities. So I mentioned just this background context so that as I get into the kind of innovative technologies momentarily, you have a sense of why COVA, what COVA is doing and why we're doing it, and why these new technologies and sensor-based monitoring is a useful innovation. So broadly speaking, currently we serve close to 2,000 communities across El Salvador, Honduras, and Nicaragua, and we work closely with community water boards, which are elected groups of individuals who are responsible for the day-to-day operation, maintenance, tariff setting for gravity-fed, predominantly water systems. So these are usually tanks fed into distribution systems with home-piped connections. Typically, these systems exist as COVA enters into a new community, but there is no form of water treatment. And so we are working with these water boards to implement inline chlorination. You can see just slightly there a PVC chlorinator, which is just a pass-through technology that water passes through, dissolves the chlorine, and then that chlorine disinfects the water across the distribution system. So currently, the majority of our program relies on frequent visits to communities to continue to monitor and ensure that these chlorinators are performing effectively and are actually disinfecting the drinking water, and ultimately resulting in safe water and positive health outcomes. So that being said, measuring free chlorine residual is either labor intensive or expensive. So labor intensive, I mean here showing this picture of a simple DPD reagent test where you're quickly measuring the color change of water after you add a chemical, and that indicates whether or not there is or is not chlorine and to what degree. However, this requires a physical visit to the actual community to take a water sample, and it also only tells you in that moment in time, right? The second you leave, it's no longer telling you whether or not the chlorinator is operational. It may have stopped working mere moments after this sample, and it's no longer indicative. On the flip side of that is where we get very expensive with inline process controllers or measurement devices such as this kind of Hawk system here, which perhaps is measuring free chlorine residual in real time, but is thousands of dollars, requires access to a significant amount of electricity, and is not really very well designed for placement into a water tank in a rural community, right? So this is the problem space that we're working in at COVA, right? We're very reliant on these routine free chlorine residual measurements that our technicians are making on a monthly basis in each of these 2,000 communities. You can imagine that that's a pretty considerable amount of labor, and it's pretty critical to ensuring the impact of our program. So we've designed a technology, a solution, using a variety of off-the-shelf available sensors to measure a surrogate of free chlorine. So what we're trying to do is measure the effectiveness of the treatment, right? This is a process measurement rather than a measurement of the actual bacteria health indicator. So what we're doing is measuring remotely pH, oxidation reduction potential, and then flow or tank level, just to give us a sense of how much water is in this system. This is kind of a mock-up of what a rural tank looks like. You can see there the chlorinator that I mentioned before, with chlorine tablets inside of it. These sensors are then installed in the tank itself. And then there's usually a data logger unit with a solar panel, and all of this is transmitting data using a cellular modem. Here's a step forward showing you kind of the labeled diagram. So what we've done is we've piloted this across 4 communities in Honduras. I should mention that all of this was a pilot study done in partnership both with COVA, the University of Iowa, and Xylem, the sensor company. So Xylem provided all of the hardware technology shown here. And over the course of this year-long pilot, what we did is we paired these sensor units across 4 communities with free chlorine residual measurements. So going back to those manual measurements, taken 4 times per site per week. So this allowed us to create a data set, right, of this surrogate measure for chlorine and actual measurements of chlorine. And I should mention oxidation reduction potential, not to get too into the weeds of the chemistry involved here, but chlorine is an oxidant. This is how we're disinfecting the water. ORP just measures the magnitude of that oxidation process. So in a water system such as this, where there's no other oxidants being added, we can infer that if ORP is changing, that's due to chlorine being added rather than any other potential oxidation process. It's not a perfect measure, but in natural water systems that are otherwise free of oxidants, we can make this kind of assumption. So then using all of this year-long worth of data across these 4 sites, we built a regression model which allowed us to determine whether or not free chlorine residual was above or below a WHO piped water threshold. So we use the threshold of 0.5. There are a couple of different thresholds depending on where you're at in the distribution system, but what's important to remember here is that these systems are being installed at the tank. So we're presuming that we need to maintain disinfectant residual across the entire distribution system. So we're aiming for this slightly higher 0.5 measurement. And we've found pretty strong results that allow us to indicate whether or not it is above or below this threshold. And so we're considering these low free chlorine residual events and adequate free chlorine residual events. This figure here shows in the black line is going to be that ORP value that I mentioned before. These shaded red boxes are going to be events that our model indicated were low chlorine or insufficient below this 0.5 milligrams per liter. The dotted red lines are going to show you actual measured free chlorine residual, low free chlorine residual events. So these are based on the grab sample taken by a technician. And conversely, the green dotted line shows you actual measurements of free chlorine residual above this threshold. So what this plot is broadly showing you is that over time, and this is a couple of month plot, you can see that this model correctly classified and confirmed both low chlorine events as well as adequate chlorine events. All of this then in turn fed into a text message alert system to actually engage directly with end users and technicians to alert them when these events were occurring, which would then motivate a visit to the chlorinator to ensure it was working correctly and determine perhaps why it wasn't working correctly in the case of the low free chlorine residual events. This hopefully gives you a picture kind of the technology that we're working with at COVA and how we're looking to expand this. Currently, this is just a pilot of 4 communities. Again, we're in 2,000 communities. So the next steps include things like thinking about how we can actually right-size this technology, right? We've used the highest quality ORP sensor possible, the most expensive one. Now can we take a step back and perhaps swap out some of these components for more affordable pieces and actually see if this is scalable across an entire program region, and if that comes with improved outcomes for water safety, which is the driving end goal. So I will leave it there. I think there'll be some opportunities throughout the panel to get in a little bit more to the results, and also hopefully this sets the stage. I think my fellow panelists are going to speak a little bit more to E. coli and some of the other indicator bacteria and things that we might be looking at that are indicative of the actual health risks, whereas hopefully this is a complementary approach to kind of the process and the treatment that allows us to control for those. So yeah, I will hand things off to you, James.
Thank you, Megan. Great. Okay, so now we're going to move on to tryptophan-like fluorescence, or TLF. So TLF is a type of fluorescent organic matter that has identical fluorescent properties to the amino acid tryptophan. That being that it fluoresces at 280 nanometers and emits about 350, 360 nanometers. And throughout the 1990s and 2000s, it was shown that it was a really good indicator of wastewater in the aquatic environment. We also know that E. coli cells in the lab directly emit TLF, primarily because of the tryptophan residues within the cells. And E. coli is actually used for the industrial production of tryptophan. So given these 3 bullet points, about 12 years ago now, we decided to start to investigate whether we could use TLF as a way to assess fecal contamination risks in drinking water. Now, that also coincided with some technological breakthroughs. Previously, we'd been stuck in the laboratory, but 2013, we started to see the first commercial fluorimeters coming onto the market. That's because we started to be able to produce low-power LEDs, so you could power these sensors just using AA batteries. So for the past 12 years, I've done quite a lot of work roaming from water point to water point, testing them for fecal contamination risks, and also using the sensors online. And the key advantages of this technique is you get an instant result. So with an instant result, you can take immediate action. It's completely reagentless, and it can be as simple as putting a sensor in a beaker of water. But now onto some evidence. So the way we've been trying to demonstrate the value of the technique is to compare it against fecal indicator organisms at drinking water sources. So this paper here, we collated all the published data at that point in time, where we had paired TLF and fecal indicator organism data. So it was about 560 sites from 4 different countries, and those were 4 separate studies, and in their own right, in each of them, there had been a good relationship between TLF and fecal indicator organisms. But we wanted to know across both groundwater, surface water, across those range in climate settings, whether TLF was still an effective indicator of fecal contamination risks. So here are the data. So on the x-axis, we've got fecal indicator organisms, and they're in log categories. The y-axis is a TLF, the natural log of TLF. And it's pretty clear that as our fecal indicator organisms increase, so does our TLF intensity. And the correlation is actually really quite strong here. The Spearman's row correlation is 0.8 across the data. And then we also wanted to see if we could set a threshold to indicate contamination. And so we looked at a threshold of 1.3 parts per billion tryptophan, and that was to determine whether a site had at least 10 colony-forming units per 100 mil. And using that threshold, false negatives were 4%, so it was actually very, very effective. False positives slightly higher, but there's good reasons for that, about 18%. So, we've been really happy with the results so far, but then, we should also think about what else we could do. If we were visiting, that hand pump on the screen there, how could we assess whether that site was fecally contaminated when we're there and communicate those risks to that user? So this was a study we did in Uganda. So we've got 6 different in-situ approaches. We've got TLF, we've got humic-like fluorescence, we've got sanitary risk scores, total bacterial cells using flow cytometry, turbidity, and electrical conductivity. And the figures you're seeing, you've got your AUC, your area under your receiver operator curve. And so that's an assessment of how good each of those variables are at predicting the presence, absence of fecal indicator organisms. So 1 is a perfect classifier. A figure of 0.5 means it's no better than tossing a coin. Okay, so we see that TLF is the best approach for both the presence, absence of fecal indicator organisms, but also their enumeration. It's the most correlated. So then we can then carry out the same analysis on other data sets, so data set from India and a data set from Zambia, and TLF is the most effective in-situ indicator on every occasion. We can also see how other approaches, such as your sanitary risk scores, are quite inconsistent. They work reasonably well in Uganda, but over in India, where actually a lot of the sites looked pretty similar, they were no better than tossing a coin. So TLF is the superior approach in situ. And then we can take measurements online. So this is at public water supply boreholes in the UK. We set 5 of these up, telemetering in data at 2-minute resolution. And the figure on the top there, the black line is your TLF. Then the water company is taking measurements every week for E. coli. So what we're just trying to demonstrate here is, how much you can learn by generating this high-frequency data. And that high-frequency data, in this instant, correlated very well with E. coli and was also superior to turbidity, which the water company were using at the time. Yeah, that's it from me. Over to you, Whitney.
Awesome. It's this button, right?
Yeah.
Great. Thank you so much, James. So I'm hoping I'll be able to harmonize a little bit of what Megan has been speaking about, and then James as well, into some of the research we're doing at CU Boulder and some of the ways that we've commodified that into a product for deployment as part of Verity. So this has been spoken about a little bit already, but just to give another overview, Measuring microbial exposure in drinking water sources and recreational sources is significantly motivated by public health and protection of the public, as well as oftentimes required by regulatory agencies for compliance. And typical methods for monitoring microbial exposures is done with fecal indicator bacteria, and this requirement for monitoring, it must be done using laboratory-based methods to quantify concentrations of E. coli, which is the typical fecal indicator bacteria for drinking water supplies. Unfortunately, as we've sort of mentioned, microbial exposure and measurement with lab analysis, it takes significant consumables, time required to send a team out to the field to acquire those samples, time to perform laboratory analysis, and eventually it takes anywhere between 18 and 24 hours to go from sample and analysis to getting any sort of enumerated values of E. coli. That makes these data not very actionable when you are trying to act on the efficiency of a water system and protect public health. This is, like James was mentioning, where tryptophan-like fluorescence can come in as a more real-time indicator of microbial contamination. So our company Viridi, as a spin-out of the University of Colorado, has developed a sensor that is a real-time E. coli monitoring sensor utilizing tryptophan-like fluorescence. This is work that's been long dated by my predecessors at the University of Colorado, specifically Emily Bedell and other researchers that have taken a lot of time to take TLF as an indicator and pass that along to do more accurate estimations of microbial exposure. A couple of key features of the sensor is that it is aiming to categorize fecal contamination in risk scores in accordance with the WHO, meaning these are categories of 0 or less than 1, 1 to 10, 10 to 100, etc., following orders of magnitude, which correlate to risk of microbial exposure in water. So this doesn't just output relative fluorescence units of tryptophan, but actually takes that one step further and hopefully categorizing that risk. It is built using a machine learning model, so it doesn't require regular calibration. Data from around the US as well as around the globe has been acquired to train this model, making it not site-specific. And it is designed for continuous in-situ use, really taking advantage of getting more spatially explicit and temporally dense data. It utilizes a battery or solar panel connection that does not require typical maintenance, as well as the machine learning model taking into account factors such as biofouling. And because of the engineering that has gone in behind it, it retails for considerably lower cost and focuses on a single one parameter rather than other similar SONs that utilize multiple parameter analysis. So looking a little bit more into some of the applications of this sensor, we focus primarily in two areas. One would be real-time monitoring for drinking water supplies, and the second being monitoring of recreational water supplies. So I'll start from the left. These two pictures on the top and the bottom are monitoring of drinking water supplies. The first of these applications we have in piped water systems that come from groundwater extraction. An example of this we have piloted in Isiolo, which is in northern Kenya. This sensor is installed following an inline chlorination system to ensure that the water that is now sent to communities following chlorination is microbially safe to consume. Second, in that bottom left picture, you see one of the sensors applied in a community life straw filter in schools for drinking water for school children outside of Kigali, Rwanda. On the right side, we have several applications both in high-income countries in the United States and in France. The top two pictures are deployments we have in the Charles River in Boston, monitoring recreational water quality, and then in Chicago, Illinois, which I will pass on to Elena to speak further about later. We also have these sensors installed in a network along the Seine in Paris, where those data are helping to inform, in the future, the safety of recreating in the Seine. So one of the most important parts of the motivation behind this sensor is to ensure that water quality data are more actionable. And this is allowing for water quality professionals, whether they're part of municipalities, advocacy groups, or consumers, to act on water quality data as it comes up rather than retroactively. So the sensor is connected to a dashboard that is able to represent both raw signals that you get from the sensor as well as more semi-quantified E. coli units. Here are a couple of metrics we have of the performance of the sensor thus far. The first chart that you see on the left, I guess I should note specifically that these data are preliminary, and it has come from a number of our different testing sites that I had mentioned previously, including the city of Paris, on the Seine and the Marne, Chicago and the current team on the Chicago and Calumet rivers, the Charles River watershed in Boston, Cleveland Water Alliance on Doan Brook in Cleveland, Ohio in the US, the city of Boulder along Boulder Creek in Colorado, and then our life straw tests and MWA tests in Kenya and Rwanda. And I apologize, those should be flipped. Life straws in Rwanda and MWAs in Kenya. So getting a little bit further into this performance, the left chart, as you can see, on the x-axis, you have the model estimated E. coli in colony-forming units per 100 mils of water. And on the y-axis, you see the lab enumerated E. coli. These validation tests have gone in a similar way as Megan had mentioned, where you take a ground truth sample and enumerate these samples for the laboratory grade methods. This has been done with both membrane filtration and a common enumeration technique called call alert. And then sent through the data collected on the sensor side is sent through the machine learning model developed by our research team as well, to also accommodate for other factors that are influential in E. coli contamination, such as stream flow, rainfall, and also taking into account sensor location. Oftentimes these sensors are deployed in networks that allow each sensor to learn from the one prior to it or others in the network, increasing the ability to predict. So as you can see, we have around a 20% error in these predictions, both in your training data set, which is used to train the machine learning model, and then the test set, which is used to validate the accuracy of the model. The second chart you see is a confusion matrix of prediction. I had mentioned previously that this sensor is designed for estimating E. coli concentrations in accordance with WHO risk categories. We also have a version that defines a threshold for safety of swimming. Oftentimes this lies in the range of 1 to 300 CFUs per 100 mils, which is what you see here, 300 as that threshold. Similar to as James had mentioned, you see the highest level of accuracy in the three categories where the model is predicting the same as the ground truth is telling us. The upwards categories are the ones that are of highest risk, where you are underestimating the true contamination, although we see that at less frequency, about 4 and 7% based on this model. This is something that we're still considering as far as making sure that we're getting a large and vast training data set to accommodate for all of the different categories. As you can see, most heavily you see that between 10 and 300 range of CFUs, which we want to make sure that we're continuing to get a large data set. However, these data, as I mentioned, are trained on all sorts of different locations, ideally making sure that the data are representative of a large amount of samples across diverse contexts. So that's all I have for you as of now. I'm also part of a technical working group that COVA and a couple other convening organizations are focusing on for potentials of remote water quality monitoring in various applications, and we will be publishing and speaking more on a roadmap for what these different technologies and applications look like in the future. And now I'll pass it along to Elena.
Great. So I'm going to eventually bring us all the way back to water quality monitoring, but by way of a detour first, I just want to be dot connecting that this panel represents kind of a microcosm of the water innovation ecosystem and what it takes to bring solutions to scale in any different field context. Whatever part of the world we're trying to do it in, we have the innovation, the research to ask and answer the questions about what techniques and are going to work the best and be most effective in which settings. We've got the corporate partners that are helping to scale it, the nonprofits that are helping to build community and broaden the awareness and access. But what I have done at Current and what my team does every single day is try to build ecosystems that work to speed innovation and reduce the frictions that Megan, James, and Whitney all talked about today. So our job, we have 3 parts of our mission at Current: grow a circular blue economy, and I'll talk a little bit more about what that means, accelerate water innovation, and that's by helping to de-risk, cut out the friction, cut out the cost, cut out the time that we heard about in the development and deployment of these innovative solutions, and then solve water challenges, like the challenge of understanding, are our rivers safe to swim? Is our water safe to drink? So those are some great examples of the kind of innovation work that we do. I mentioned in the beginning that I am wearing 2 hats now. One recently has been, as a result of this investment from our U.S. National Science Foundation, a big federal funding backer, to support our work to build a regional innovation ecosystem around water. And I'll talk about why that's important, but you already heard the value of network effects when we're trying to deploy sensors and gather more data is really important, but so is the value of having multiple places to trial those technologies. So building a bigger network of people who share this vision is really critical for us. Our regional innovation engine is, again, backed by the National Science Foundation, but ours is focused on a very specific set of technologies that are helping to drive resource recovery and circularity in water, not just in the Great Lakes, but around the world. And so we are hoping to build an innovation ecosystem of actors in the Great Lakes region that helps to recover critical minerals and resources from wastewater, helps to recover and capture energy and carbon, nutrients, which we've talked a lot about at this conference, how much that is a challenge when they're in the wrong place and a benefit when they're in the right place. Other critical rare earth elements like lithium, cobalt, and nickel, the elements that are so critical to driving our energy transition, but also water itself, which has been a massive challenge in the Great Lakes region where we are water abundant, but don't do nearly enough to manage those resources in a circular way and have a long way to go to sort of catch up to the water scarce world in the way they've been able to manage those resources. Our region of service, just briefly, I'll spin through this. We work with partners across a range of states, are concentrated in these 6 Great Lakes states in the United States. And our partners span local governments, state governments, research institutions, startups, big industry partners, education and workforce development training partners. And we are quarterbacking that effort because as a nonprofit, we are an independent network builder, and we are able to bridge and connect and help to, again, absorb and manage some of the risk that our partners take on in trying to bring these technologies to market. The ways that we manage our track record and track our impact is in the funding and resources we're able to raise and invest in these critical water technologies, the pilots we're able to bring to scale, and the startups we're supporting. We're also, in recent years, been really measuring the number of students and adults that we're training and educating for careers in the blue economy. There are so many ways to work in water, and that's a really important frontier area of work that we're spearheading. So to turn over to our water quality work for a moment, just a quick show of hands. I'm interested, who in the room has been swimming in an urban river or lake? Just show of hands. That's great, okay. Special audience here, I think. That's great. Okay, so how many people did that this morning for World Lake Day? Anybody else? Any swimmers in the room? Okay, well that was a terrific way to start the day. I got to go out and do that. So why is this so important? We've been talking about these fundamental challenges of getting clean, safe drinking water, sanitation that works all around the world. Certainly that's more important than swimming in a river or being able to kayak in a river, right? Except that we're reaching so many more people in helping them understand what it takes to manage that water quality when we connect on something like recreation. It is a way to, capture the attention and awareness and interest of people all over the world. It's a very accessible way in to understanding the problem of clean water and management and what it takes. So the reason our organization actually got into water quality monitoring in the first place is it was a great way to show the public in a way that connects to something they care about, our Chicago River, a big asset in our backyard. What's going on in the river, and what does it actually take to be able to answer the question, how's the river doing today? Seems like such a simple question, and yet it's fundamentally, you've seen here the work that goes into understanding what are the best proxy measures for the contaminants we want to monitor? Tryptophan-like fluorescence, right? How do we build a low-cost sensor that we can deploy so we get lots of data and not just a few different data points? This is a non-trivial problem. When we started this work, the sensor setups cost over $25,000 per node. That's too expensive to deploy even in a high-income city, in a high-income country. We just can't do that. We can't get the amount of data we need, so there's a real need to bring down that cost and think about how to build these at scale. So we built this platform called H2 Now Chicago, H2 Now because it's about getting real-time water quality data in our urban river, and we call it a weather app for the Chicago River. So you can scan this QR code and see every single day, every 15 minutes, how's the water doing in all 3 branches of the Chicago River. That's important because we found out that water quality is highly variable, even in the same city, even in the same river, and that's fascinating to us. Like, why does the water quality vary so much, and how do we think about how to manage and support even better improvements over time? But then also, we've recently added a monitoring setup in the Calumet River, which is really important because it's a different waterway in our watershed, acts very differently than the others, and it's a really important one for us to steward. It's connected to heavier industrial areas, and also goes through communities where a lot of people live. And so building this weather app for the Chicago River involved the engagement of research partners, the startups. Actually, it was a UK company called Proteus Instruments that built the tryptophan sensor and probe, the multi-probe that we have deployed to power this. But we also invested a lot in the front end, just being able to build a super simple interface that help people understand today is a low caution day to do something like kayak in the river. And we've pegged our gauges to the EPA primary contact standard for waterways, which just means that we're trusting a government source to say, this is what good means, and we are tracking our data to conform to that. This is really important because over time, our Chicago River, like so many other rivers in the United States that flow through cities, have been used as dumping grounds for industry, and also receive a lot more runoff with the extreme weather events that we have in the Midwest these days. It's really important for us to understand how that quality is fluctuating in real time as the increase in recreational users is happening every day. We really want to see that, again, because it connects to more informed and engaged potential advocates for water quality all over the world. So what we've done so far, again, I mentioned 4 probes so far have been deployed on 2 Chicago rivers. We are monitoring this microbial water quality, and it's now not just our Proteus sensor, but we actually have deployed, as you heard Whitney say, the Virity sensors as well. So we're understanding how they perform in comparison to each other, and what are the differences, and how can we think about bringing that to scale. The data assessments are updated every 15 minutes, which is a real achievement for us. It's meant having to think a lot about the telemetry, the data systems. It's a lot besides the probe itself that communicates this information to the public, which again, that's the most important thing for us here, is to be able to share this in an actionable way. By the numbers today, we have actually trialed more than 9 technologies on this platform. So the reason that we're doing this work, besides, again, demonstrating to the public in Chicago that this matters, is that we want to see our river become a test bed and a place to trial other kinds of technologies that can help us improve the way that we understand and manage our urban rivers. And so we've trialed sensor technologies. We are building, through our work with Great Lakes Renew, a connected testbed network of real-life urban river sites across our Great Lakes region, but also trying to connect to other kinds of pilot testing sites with utilities, with industry, things that will help these sensor technologies test out and prove their usability in a range of different settings. That's really important for the companies as they try to go to scale in a lot of different contexts. And we're really broadening public awareness, and that, again, is very important for us. We have a big swim coming up in Chicago at the end of September. For the first time in more than 100 years, we're going to be swimming in the Chicago River. That's really exciting. It's part of this broader swimmable cities movement that has been gaining a lot of traction, but it's really important for us to know on any given day, how's the river doing? And so we're excited to be using H2 Now Chicago in that context, and that's also really helped raise awareness for the importance of water quality monitoring more broadly. So that is what we're up to. And again, I want to just make the connection. I hope this really lands with everyone here that while we're building this innovation ecosystem in the Great Lakes region, in a freshwater economy, in a very high income country relative to many places, it's about the innovation ecosystem that can build solutions that can be deployed everywhere. And you see that on display here on this panel. And a lot of what we're doing is trying to just reduce the friction, increase the awareness, and speed these solutions to market, because the world can't wait for solutions to the water challenges we have. So thanks so much. I will leave it there, and I look forward to lots of questions and dialogue with this terrific panel. Thanks. Back to Alex.
All right, thank you so much. That is excellent. I think you all saw the huge range of applicability for some of these new technologies, and also a lot of need across low and middle and high income applications. So would love to move to a panel discussion, but first, obviously, you wouldn't be here if you weren't yourselves subject matter experts in a lot of these things. So would love to take a pause and just see if we've got 10 or 15 minutes of questions from you in the audience. So don't be bashful. It's way more exciting for you and us if you ask some questions and get some responses. So anything clarifying, anything that you'd like to know from anyone? Yes, right here in front. Oh, here we come.
Hey, thanks everyone. I'm just going to ask 2 questions. Why not? First of all, is cost. I'm curious for everyone. What's the cost of your technology? And then I'm curious, so 3 of you are talking about tryptophan like fluorescence. Like, are you working together? What's the difference between your technologies? Like, what is that? I don't know. What does that look like? Is there a competitive advantage in some way or another? So just curious about that.
Mm-hmm.
I can take cost first on this. So the cost of building this sensor is significantly less than others. You heard Elena mention the Proteus sensor and other similar fluorescence-based sensors that monitor tryptophan. Those tend to be on the order of magnitude 20,000 USD. These are approximately 1,000 USD for manufacturing, and the business model, while it likely varies context to context as far as high income to low income, would be to lease these as like a data service for $200 a month. And while there are definitely different definitions of low income versus high income and what low cost actually means, what we're really trying to lean into is the benefit that you get as a cost effectiveness of having real-time measurement, dense data that are actually actionable and influential in monitoring and measuring. And I will mention that I didn't mention in the presentation, these sensors that are installed in the low-income context are designed hopefully to be a monitoring and verification tool for projects that are earning carbon credits that not only have to deliver water, but make sure that that water is safe. So this will be proposed as a digital monitoring tool for that as well. And then I guess to extend on the collaboration, there are, obviously we're partnering directly with Current, and that is something that's lovely and we are both getting a lot out of. Related to James and BGS work and all of the research that's been done, this sensor is very predicated on research that James has done and previous researchers. And I guess to put a little plug, we're really hoping to collaborate with BGS and James further. So that will be something in the works.
So, I mean, the first generation of tryptophan-like fluorescence, they were about £10,000 a sensor. But we're now reaching an inflection point where the costs have dropped so much that you are seeing an order of magnitude drop in costs, and $1,000 sensors are now achievable. But equally, there are no ongoing costs. Yeah.
And to hop in on costs related to the kind of the chlorine sensing unit that I mentioned. So using just like research grade, high quality components like those in the pilot, we're looking at $5,000 or $6,000 for a unit, all in solar panel, data logger, et cetera. we're aiming about a magnitude lower currently. And that's achievable with kind of some of those lower cost components that I mentioned. So right now we're part of a pilot project that's happening in partnership with the Global Water Center to test out basically this exact technology, but just a lower cost version of each component to hopefully bear out what we believe to be true, that it will perform the same. The big question is lifespan, right? How long are these sensors going to last in situ? And that's pretty hard to tell without multiple years worth of data. So that remains to be seen. And then I think I'll quickly plug, and I'll plug this again probably later, but what Whitney already mentioned, which is a technical working group around sensor-based water quality monitoring. And I think one of the goals is to build out a roadmap looking forward for what needs to happen to make this feasible, both in low-income contexts, but also in high-income contexts, and what kind of research it's going to take to go into that across a variety of different parameters. And I think one of the driving factors is, for us particularly in lower-income settings, is cost. It's going to be, how can we do this and make it cost-effective, like Whitney mentioned, make it affordable enough that it replaces or complements closely the manual monitoring that's already happening.
Yep. And I'll round it out. Current doesn't develop any technology ourselves, so our IP is in the process and the platform, but we haven't talked a lot about the labor costs. So the unit economics of the sensors really does matter for us, because if we're thinking about, the question we're trying to answer is, what would it take for every city, every community to be able to know the quality of their river all the time and get that actionable information on demand? What does that cost, and who can pay for it, right? So what we've gotten to understand over the last 5 years that we've been doing H2 Now is the cost of, we're understanding how long this older generation of tryptophan sensors lasts, and how much it costs for our team to go out and do sampling. We get a lot of in-kind contributions. This is a partnership with our utility, our wastewater utility, which is doing other kinds of water quality monitoring. So that partnership building is really important. So we're really still, I think, trying to understand the true ongoing cost of all operations, maintenance, the research partnerships that we get to help us validate. We have a working group, a technical working group that helps us make sure, again, that the sensor data is valid. We're putting this out to the public. So all of that wrapped together for us costs our organization like north of $150,000 a year for this whole deployment, which again, we then go raise funds, deploy funds, and we hope that that can really come down. And through our network, we are now deploying with the same sensors. You heard Whitney mention Cleveland. That's part of our connected testbed network for Renew. So being able to build those partnerships in other cities, understand cost comparison, how do we just bring this down overall, and find efficiencies in like the labor and process and other components of it, which are, for our team have been a lot of time figuring out how does this all fit together, what's the most efficient and effective way we can do it. So it's a great question.
Thank you so much. Right here.
Yeah. Well, first of all, just wanted to commend all four of you. The work you're doing is incredible, and it was cool to see all the collaboration between all of you and building off of each other and partnering with each other. So thanks. It's a very inspiring panel. High-level question about the outcomes of monitoring. I was hearing two main outcomes. One is that public use of okay, it's safe to swim in the river, and we know that today. And the other outcome of identifying when there's downtime on water quality equipment. So Megan, I had a question for you, and kind of applies to the panel overall too, but I was curious what impact you're seeing from this monitoring on the uptime or the percent uptime for that chlorination or other devices. I guess how has that outcome come about? Thanks.
Thank you for that question. I was hoping someone would ask, and I was hoping I would have a chance to speak about this. So I had a slide that I ultimately removed, but one of the things that we rolled out across the end of this pilot, after building out kind of these algorithms across each of the 4 pilot sites, was a text message-based alert system for both our technicians, but also for the water board member who's actually responsible for maintaining the system, right, maintaining the chlorinator and refilling it with chlorine. And what we found was that over the period of time when those text message alerts began going out indicating a low chlorine event, that we saw 30% fewer lapses in chlorination, and those lapses were also shorter in duration, meaning that, at least the presumption, meaning that either the plumber, the member of the water board or our technician was able to respond quickly enough and resolve whatever the problem was. In most cases, the problem is simply that the chlorinator tablet hadn't been replaced in time. And this is a pretty big time-saving mechanism because these tanks are typically, 2, 3, 4 kilometers away from the community and away from the water board member's home that they're responsible for. And it's a lot of effort to hike up just to find out that the chlorine tablet doesn't need to be replaced yet. So these text message alerts can essentially replace that whole guess and check mechanism. And at least anecdotally from qualitative feedback we've heard from these water board members that this is a much more positive experience for them than having to hike out and find out and know that they may have gone hours or days without safe water. So at least across the pilot period, we're seeing really positive water quality outcomes and user outcomes.
I love this question because I've never thought about the downtime on the river, but that's actually a great way of thinking about what happens when we have combined sewer overflows or events, big massive rain events where it's not safe to recreate in our river. And it's not healthy for other things either, but like we're thinking about this kind of public use idea. So what's really interesting about the real-time water quality monitoring, it complements our public notification system about combined sewer overflows. So when our sewage system is overwhelmed, usually by a storm event, a rain event, and releases sewage into the river, there's an alert system that you can subscribe to. So that public notification's already happening. But what we've seen that's really interesting since we've been gathering data through H2 Now, we can see in real time the correlation of those spikes happening, sort of syncing up of the public notification, which is just a great thing to know, like that's kind of like almost is the public notification system working? But most importantly, we see when it returns back to normal. And that's the thing that the public notification system doesn't do. It doesn't close the loop yet with the humans who want to know, okay, great, but is tomorrow a good day to kayak if today wasn't? Because tomorrow's Saturday and I want to take my family out, or I want to go for a swim. And we need to close that loop to know when it's returned to normal. Otherwise, it's sort of like an alert without a resolution. And so that's what we're able to see with the real-time monitoring. And I think it's good news that often that return to normal happens pretty quickly because the river's moving, things are moving through there. But that's something that, again, until we kind of watched in real time and we're analyzing the trends, kind of couldn't see that actionable information and when it's back up.
And I think I can maybe add one more thing. I think it's really important to note that, well, first of all, we were missing an original panelist that was supposed to be here, Joe Brown from UNC. And something that has been impressed upon by him for me is not data just for data's sake, but making sure that that is actionable and there are actions attached to when you're getting data. Otherwise, these things aren't useful. They're not meaningful. So I think a great example of making that useful is the situations that we're seeing, in Chicago. Likewise, a lot of our pilots are with other, public good organizations focused on that. Likewise with municipalities, we're partnered with the city of Boulder, which has one of the only regulatory limits for E. coli in the state of Colorado. So they're incredibly invested in making sure that that's both compliance for regulation's sake, but then also for public health sake. And then pivoting more towards the drinking water focus is we have some projects, Verity and CU Boulder are partnered on projects for maintaining uptime of water systems, groundwater systems. And we've seen similar situations, as Megan was mentioning, where you do have actionable feedback on when a borehole becomes non-functional to increase the time to, or the rapidness to repair rather, decrease the time that it takes to repair those. And hoping to see analogous results when these are piloted, as far as taking action for water quality, not just water quantity. And I think that's what I have to say about that, yeah.
Great, thank you. Anyone else? Yes, one up there, if you don't mind. Oh, he's got you.
It's for the people online.
Yeah,
too, I think.
don't forget about all of our digital friends.
Yeah, I think I have a question for Megan, but maybe if it's applicable for everyone. I'm actually curious, like in the future, like scalability of this project. So my first question is related to disinfection by products. Is this considered? How much, how it looks like? And my second question is related to, I think some continents, if I'm not mistaken, for the European Union, people that don't like chlorine for disinfection. So how can we like make it work somewhere else? Thank you.
Yeah, those are both great questions. So absolutely, disinfection byproducts certainly keep me up at night. I mean, generally, at least at COVA, we kind of subscribe to the WHO standpoint, which is that the acute risk of diarrheal disease is much higher than the potential chronic issue related to disinfection byproducts. That's not to say we ignore them. It's to say we're aiming our target chlorine dose to achieve both outcomes, but to focus on the acute risk. So we're always very cautious about not over-chlorinating, and also we have internal protocols around chlorinating during high turbidity events, which are related to increased organic load, which are correlated to the potential formation of disinfection byproducts. So it's all to say we're trying to maximize the health outcomes and minimize immediate risk while keeping in the back of our mind at all times the potential chronic risk. So great question. I think related to countries where chlorine is not the disinfectant of choice and other methodologies are used, it depends. In the case of these sensors specifically, if other oxidants are being used, these ORP process sensors would still be useful, presuming that there's no naturally occurring oxidation process. This technology, and one of the reasons we're doing additional pilot studies with the Global Water Center that I mentioned, is to test this out in a couple of different contexts to make sure that the background chemistry of the water before you're adding chlorine is not significantly influencing the outcomes. We're seeing similar outcomes across a variety of different sites in Central America, but that's not to say we're going to see the same thing in Uganda and other places. So that's one immediate research area. But the other is that you're correct that if you're not doing some kind of oxidative process to treat your water, these sensors won't be particularly useful, but there might be and are likely other process mechanisms you could measure instead. And it would also then be when a tryptophan-like fluorescence sensor, like my fellow panelists have spoken about, would be more useful because then you're measuring your kind of outcome risk rather than the process itself. But thanks for the questions, and I don't know if either of you guys.
No, I was just gonna. You can actually use a fluorimeter to control your chlorine dosing as well.
Exactly.
Because it would measure the amount of organic matter.
It's a good
Collaboration. Good research topic.
Great. Yes, one more. Thank you for this.
Yeah,
I've got questions, but these are exciting to receive. So very much appreciate your engagement.
Hi there, Robert Bradburn. I'm from the UK Environment Agency. So I was fascinated also about this idea of downtime of a river. It's a matter that we manage in England. Mm-hmm. And I suppose my question is, with the new sensors coming online, we know that, being polite about it, the epidemiology between fecal indicator organisms and whether it's safe to go swimming is 50 years old. What are the opportunities for actually updating our understanding of what it means to have bacteria in water which you are using for recreational use?
Oh. Pass that along to you first.
Yeah, no, I think that's such the right question. It's such a good question. I think it speaks to, I'll back way up, and the framework of this regional innovation engine we're running is all about bringing end users to the forefront of setting a research agenda and helping to drive commercialization of technologies that already have demand, whether it's from industry, from utility, from community. So I think of this work, the water quality work, as having many different potential end users, because our utilities, I mentioned them, they are a partner. Our Metropolitan Water Reclamation District and our City of Chicago Department of Water Management, they are collaborators and partners in this. They have an imperative to be able to deliver this safe water for everyone, and so they are partners. The public and the community in this case is a really big audience for this. So I think, again, like through this engagement, raising awareness, building that demand for understanding what's in the river, how do we continue to lift the floor of understanding on what matters, which indicators matter the most, how do we get to the answers and faster, right? Like that's kind of our driving framework. So I think having like public demand for different information is really, really, really important and part of the story. And then hopefully you hear it coming from researchers too. Great question.
Yeah, really good question. If I can just add a little bit, unfortunately speaking as an engineer, not an epidemiologist, we were actually asked a similar question in preparation for this panel, namely that was, what is a breakthrough that you believe could accelerate deployment of these sensors? And your question is actually the answer that I had envisioned of, when you're using an indicator like tryptophan-like fluorescence, you're kind of going several steps back from the outcome that we actually care about, which is public health. You're saying, okay, if I'm worried about public health, we're setting an E. coli and other fecal indicator bacteria thresholds, which then are even further displaced from TLF. And so what I had envisioned as something that I think would be really beneficial from a public health standpoint would be to do more direct correlations between what you're seeing in the river of a tryptophan-like fluorescence value and correlating that to negative public health outcomes. And while that might be a really challenging public health study, all that withstanding, I think that that's something that would be really beneficial, not only from a public use standpoint, but also for a regulatory agency looking to be willing to adopt and take on a different kind of monitoring rather than laboratory sampling.
Yeah, yeah.
Solid.
Question.
All right. Anything else before we jump into kind of a panel discussion? All right.
I have a question.
Yes.
No, it's
Please.
for my panelists.
Yeah.
When you're talking about tryptophan and trying to explain tryptophan-like fluorescence, is it just an American thing to go straight to turkey after Thanksgiving and talk about, like, the thing that makes you really, really sleepy after you eat a Thanksgiving turkey? How does that work in the UK?
Yeah, I've never had that in the UK.
How do you explain it to your friends and family?
But Canadians also make that same point as well.
Oh, interesting. Interesting. Yeah, it's like my go-to default.
Wow.
Yeah.
Unfortunately, I'm a vegetarian, so that's actually never been something I've thought of, but that's something I'll keep in my toolbox in the future.
All right, great.
But we were talking about how you communicate a reading, and units and what units you use to communicate that reading. So do you communicate a CFU per 100 mil reading, or do you report tryptophan units, which are completely meaningless?
Yes,
exactly.
Everybody.
Yeah.
Yeah. The turkey scale. Oh.
Great. All right, we'll jump in. And we have, what do we have? About 20 minutes or so. So, as you heard, I think, especially Elena mentioned Chicago, a global city, certainly a city with a lot more resources than many around the world, is the first for a lot of this real-time sensing. And so, this is to all panelists. Clearly, real-time or near real-time monitoring of fecal contamination is pretty rare globally. What are the key barriers that you see or that you hear in your global networks? Are they technical, financial, institutional? Something I didn't list. What are the key barriers that you're seeing? Whoever would like to jump in.
Well, we've heard cost. We've heard communication of value. Those are two big ones that I think everybody has named. Finding willing innovation partners in the public sector particularly who often have a lot of the engagement or responsibility for this. And so we're very fortunate in Chicago, again, to have utilities that are willing to partner with a number of different entities, but with us, with a nonprofit, and invest in that work. And I think just having more of that innovation interest and capability, particularly among utilities, and capacity, investing in that capacity is a really big deal, because ultimately we're out here trying to prove out technology, show that there's demand and interest in the hopes that it will get picked up at scale and adopted by the sectors that are deploying it at scale everywhere all the time. And so I think when we think about who are our most valuable partners and where are the places we'd like to see more investment, it's often in those utilities.
I guess kind of coming off of that, I think a significant barrier, as I sort of mentioned, is that institutional barrier. There's, plenty of places where it's well, I guess everywhere, that it's not regulatorily accepted to use, any sort of near or real-time monitoring or proxy monitoring as your reporting. So I think that that's something, for example, in our carbon projects, these are drinking water projects that earn carbon credits. The required methodology behind that is, grab sample lab enumeration. Likewise with US EPA and other ISO standards for microbiological monitoring. So I think one thing that is trying to be pushed forward by sort of the remote monitoring side of things is what is the value add and what are different opportunities to increase your data that would be actionable and valuable beyond just, a regulation standpoint and pitching that as well.
Yeah, I think we're too shackled to culture-based methods. In 2016, UNICEF launched a campaign to try and get more rapid detection of E. coli methods, and we're here almost 10 years later. And I was looking back last night through the most recent update, and it was that because they prioritised the culture-based approaches and speeding those up, but they'd only actually managed to get up to 10 hours. And what use is that for same-day reporting or trying to encourage behavioural change? Exactly. But it's also how you benchmark these methods, which is something you're alluding to. How do you benchmark TLF? You're benchmarking it against a culture-based method, but you're not measuring the same thing, so you're never going to replicate those culture-based results. So it's how you think about risk, I think, is what needs to change.
Yeah, and I'll just echo, I think the regulatory issue is one of the biggest. I think about our contexts in Central America and how extremely useful this would be for community members and technicians to have real-time, risk data about how safe their water is that they're drinking. But we would still have to do culture-based methods to meet regulatory standards. So it's not a full solution at this time, but that's purely because the regulatory body. And I think to your point about UNICEF, I think as hopefully these technologies advance, they will become more accepted as an alternative to those culture-based solutions, and other countries will follow suit to accept those results, which will kind of allow us to meet in the middle for the community utility and the government reporting utility, both of which are key to the work that we do.
And this might be a rapid one, but would the panel think that the barriers are pretty similar across the income spectrum or pretty different? What are we seeing out there?
I think the obvious answer is that cost is going to be pretty different depending, right? But I think I still think it's a unifying force, but I think the costs that we would need to meet to push this out across 2,000 communities is probably a little bit different than the cost to deploy several in the Chicago, area. But to your point earlier, that's still critical, right? It's not critical. Trivial at all.
Yeah, and it's what are the variable costs, right? In different, because the technology costs are the same. Right, maybe relatively,
exactly.
They're not. But if you've got someone that's a payer, we care that this is $1,000 and not $20,000.
Right.
A lot. The labor costs might be very different from place to place. Your lab sampling might cost, those costs might be variable. But yeah, these fixed technology costs, it matters a lot that they come down.
Yes.
Everywhere.
Yep.
Well, I think and there's a different association with cost too. What is the cost of drinking dirty water and not knowing it? And so I think that that's one thing, particularly in the low income context, that we want to focus on is foregoing the measurement because of cost doesn't necessarily get you anywhere from a public health standpoint and from a compliance standpoint for that matter. So while we do talk about low cost as being relative, the $200 a month is not a trivial cost. Particularly in a low-income context, but are you willing to, sacrifice that and not understand? Because there's obviously significant evidence that shows when you know the quality of your water, you can more readily act on that. Whether that's, from a personal standpoint within your own home and recognizing I should use my, point of use filter, or from a larger standpoint of, within a community water system and proper management.
I think it is really interesting in the recreational context too, which would seem like it matters, less from but I mean, it's like we're swimming, right? We're swimmers. So, but like if you look at what happened with the Olympics in Paris and the water quality events that were going to cancel the swimming, and it was a whole thing, and then there was a drive to invest in understanding what was happening. And that's really important, right? Because as more people are using the water, which is great that they're back doing that, there's definitely a more informed public and a bigger demand for understanding in real time. So there's going to be, I hope, more investment and drive to invest in that, but it is really interesting to see that as usership grows and awareness that we can swim in rivers grows, how that might connect to willingness to pay.
Well, and clearly investment in a high-income setting can have a pretty rapid beneficial ripple effect down into what's possible in low-income settings.
Right, because if you've got big purchasers, trying to connect the dots across urban rivers all across, high-income countries, that's a great market for sensor technologies. Yep.
For some reason, all of the inventions that have been in for outer space, living in outer space, there's a lot of inventions that we use every day now that were created in the ultimate high-income setting, which is the International Space Station. Still staying on some of those differences because I think it's fascinating, and hopefully the audience agrees. Deployment, right? As opposed to barriers, especially for those of you that in the middle two, I would say, that have now done a lot of deployment in both low income and high. I would love your thoughts on what are the differences on deploying this sensor technology.
I can go first since James wants to mention anything. Cool. So I think obviously the primary difference would be the objective, which we've all clearly mentioned thus far, is, in the high income context in which we work so far, this is all about, recreational waters, improving access to public information, and really having the public be the driver behind changes in water quality and action behind that. Likewise, in a more low-income context in Kenya and Rwanda, where we're currently working on these, it's drinking water quality. Again, some of the more logistical things are focused on how you're deploying the sensor and where. And then what kind of maintenance goes into that. Obviously, maintenance is a challenge regardless of where you are, whether you're sending your techs from the city out to the water points or you're relying on someone who comes out very infrequently, if never. And so I think that that's a really important point. And then I guess the other thing I would mention is the matrix of water in which you're deploying. A lot of the systems that we work with for drinking water systems come from groundwater sources where you might see, less turbidity and a little bit more consistent contamination matrices, whereas in high-income contexts, in streams and rivers, you might see higher turbidity, other things like that. So those are definitely considerations for maintenance. And then I think I said the last thing, but to pile on one more thing, is data availability and transmission. Right now, these sensors are internet connected, and so they require an internet connection, and a relatively strong one. So where connectivity is limited, that can still be a challenge, and ensuring, as I've kind of mentioned, not just having this data for data's sake, making sure that even if you're looking at a dashboard that I had up here, that's tracking these contamination events, how to make that even further actionable of something like H2 Now is doing of, some sort of meter of, yes, you should drink this, no, you shouldn't, yes, you need to send out a tech, no, you don't. That sort of thing to really make it explicit, actionable, and easy.
Anything to add, James?
No, I think she covered.
Sorry.
Yeah.
We'll take the next one.
Very comprehensive.
Well,
and certainly into the last 10 minutes, I think let's go into the future. Especially James, you've been, your first research paper, it sounds like was 12 years ago. Some things have changed since then. Let's look 12 years out, and not just James. Like what do you see, if we're continuing on kind of the path and what you see as the next type of technology or augmenting forces, what are we going to be talking about 12 years from now in this whole suite?
Or we might be moving beyond TLF. In the optical sensing world, these sensors are measuring one fixed wavelength, but it is now becoming feasible to measure across the entire optical space. So there are some manufacturers looking at that, because then it's not just TLF. You know, you can start, there's an awful lot of contaminants that you can measure optically. So you could potentially have one sensor that does everything at the same time.
Could you list a couple of those other contaminants?
I mean, nitrate by optical ways. You know, DOC is an obvious one. I'll think while the others.
Anyone else? What's the crystal ball looking like for everyone?
This isn't so far into the future. It's happening now, but I think we'll see much more of it. But inline sensing and in-situ sensing for PFAS and other kinds of contaminants that we may not even understand right now, right? This is a big area of work, and there's partners in our Renew Coalition that are working on detection, but also, sequestration and destruction, which is going to continue to be, I think, very important. We haven't talked about microplastics, but that's another, big issue. Like how small are the microplastics we need to care about, and how do we find them and get them out? So some of the things on radar. And then, of course, we haven't talked about talked much about critical mineral recovery, but I think it's a very topical conversation right now, really important as we think about what are the things that are in scarce supply in our world that we're flushing away, and how could we find and recover them? So those are some of the things that our partners are working on that feel pretty frontier, but the future is sort of now. They're looking for pilots and demonstrations and thinking about how to bring emerging tech to scale.
Awesome. And I think I would almost like to shift away from just technological innovations, but looking at this sort of from a broader scheme. I think one vision that comes with low-cost sensing is really dense maps of water quality data. And so I think one vision I have for something like this that is, pretty consistent with others in my research group and, across the field is what this looks like in interaction with other forces, particularly climate change, and how, water events are exacerbating water quality concerns. And so, the idea of developing global water quality maps to highlight areas of concern, times of concern, and how this interacts with other, hydrologic and meteorological patterns for, future action, more resilient planning, and things like that.
I'll add from kind of the chlorine side, but I think this is widely applicable. I mean, I think we're going to see costs come down considerably. I mean, thinking about even 5 years ago when we were starting to build out this pilot, satellite transmission of data was far too costly to make that happen. And so we pivoted. We put all of our sensors in places where cellular connection was going to be fine. And now we probably are paying more for cellular transmission than we would be for satellite transmission. So we're seeing cost drivers continue to come down. I think the same is possible with just chlorine sensors themselves. I mean, again, 5 years ago, several $1,000s, you could go out on Amazon and get one for $100. I couldn't tell you if it's going to work or not. If I was going to redo my PhD today, that would be something I highly recommend, right? Is like a comparison across really affordable sensors to see whether they work and whether or not they're worth deploying. And if a $100 sensor works for 2 years, it's more effective than a several $1,000 sensor that works for a much longer period of time, right? And that's not a very environmentally friendly answer, but right. But I'm just saying I think cost drivers are going to continue to shift considerably, and I think we should be thinking about that in everything we do, and not just focusing on what we were already developing, but pivot to meet the sector kind of as it advances around us. So.
Plug for the technical working group on that one.
Exactly.
Hopefully that's something we'll be evaluating.
Yes, exactly.
Yep.
Thank you.
Great. Any last questions from the audience before we go to final thoughts?
Oh my gosh.
Yeah, we're there.
My final thought.
We may have just had our final thoughts. We'll see. I'm giving them time to think right now. Anything else from the audience? Thank you very much. All right, panelists, what would you like to leave us with today? Over to you.
Well, Whitney just seeded this for me, but I'll seed it one final time, and that is that we are building out a technical working group around this question really is it's building out a roadmap of what we need to think about as we move forward and move all of these technologies along. And that's really broad, and we're keeping it intentionally broad. So I'll plug this to the audience that I assume if you're sitting in this session, you're either interested in this or you think you might have some technical expertise to offer. So I would love for you to follow up with myself or Whitney, and we'd be happy to have you in the technical working group, because I think a wide array of voices is only going to continue to advance these technologies. So.
Go ahead. Thank you. I was just going to say, I think the future of this, much like everything else, is collaborative. And, while I stand up here as an engineer, we need, social scientists who are going to be working with how we're, communicating this data, how we're using it. Likewise, epidemiologists, to analyze these things from a public health standpoint, government officials and responsible, institutional parties to, really collaborate this and push this forward, which I think is very crucial. This is collaborative, just like everything else, makes it harder but more applicable and something that will be robust in the future. So that's another plug for the work that is going on in the technical working group, and that we, not only of everyone here, but everyone at this conference and beyond, would love to work with you on.
Yeah, I think one of the unifying themes of this entire week for me has just been how great it is to be in a community of people who are all trying to expand our understanding of the value of water. We all intrinsically see it, we know it, we believe it, but we're all here trying to help capture, quantify, explain, communicate, deliver that value. And so I know all the work that we are doing is in some way touching on different ways of gathering that data, making that case, delivering that value to different constituents. And I'm just very excited to be part of it and working with all of you. And I want to echo this point about building these broader innovation communities. Expanding this value of water concept to a broader and broader, part of the world just really requires this kind of collaboration, because it's in these moments where we can translate to each other what's meaningful to you, what's meaningful to other parts of the world, and just we're able to build a bigger tent that way. So it's been great to be in dialogue.
James?
Well, I mean, I would just encourage people to try new technology. Going back to barriers, the last paper I published on TLF was in 2021, and part of the reason was because you were just hitting wall after wall. You putting together this fantastic evidence base, but then it just wasn't going anywhere. So please be open to new ideas and new technology, because we could learn a lot.
Fantastic. Well, thank you so much for your engagement and your interest, both of you here in the room as well as everyone online. Have a great World Water Week in our last day, I guess, coming up on us tomorrow. And let's get a big round of applause for our panelists.
Thank you for allowing me to learn from you guys, even right here.
Thank you so much.
Phenomenal.